Welcome everyone to our webinar series, What About Privacy and Progress in Whole Genome Sequencing? This is Sharon Terry from Genetic Alliance, and we're delighted today to be looking at recommendation 2. You can find this entire series on Genetic Alliance's website under our webinars. You can listen to the 2 introductions that come from the Presidential Commission, as well as recommendation 1, which we held last month. We're very delighted today to have 3 very august speakers on this issue, and very briefly we'll just look at recommendation 2, which I'm sure that all of you are familiar with. But this one is going to consider data security and access to databases. We'll be looking at ethical responsibility, accountability, those sorts of things. The 2 recommendations that are the sub-recommendations from this really talk about funders of whole genome sequencing, research managers, clinical and commercial databases, policymakers, essentially all stakeholders should ensure the security of whole genome sequence data, and that all persons who work with it should be guided by ethical, professional ethical standards and held accountable to the state and federal laws and regulations. In the second part, essentially again talking about all the stakeholders, describes that the access to the whole genome sequence data should be stripped of traditional identifiers wherever possible to inhibit recognition and re-identification, and we certainly will be looking at that today, and that only in exceptional circumstances should entities such as law enforcement or defense and security have access to biospecimens or whole genome sequences. We want to remind people, if they're new to our webinars, that because there are so many people, in fact this one has about 200 people signed up for it, we don't have you ask questions out loud. We welcome your questions being typed into the little box in the GoToWebinar control panel. You can type them at any time, so even as you're listening to someone, feel free to do that. We'll go through the 3 presentations. We'll give the presenters an opportunity to ask questions or comment on each other's talks, and then we will move to your questions. We will aggregate the questions in such a way that we're hoping to reduce overlap and in fact put together like concepts and questions, thereby hoping to get to everyone's question. If we don't get to all the questions, what we try to do is get them answered by our speakers later on, and then you're able to get that answer from us since we're able to see who it came from. Okay, so without further ado, I'm going to just introduce each of the speakers one by one right before they speak. I'm not going to give you their entire bio because it is long for all of them. They are all very experienced and expert in the areas in which they work, but you certainly can we certainly can invite them to tell you a little more if that's important for their talk. And so without further ado, let me introduce Latonya Sweeney Phd. She's a professor of government and technology in residence at Harvard University. So Latonya, please go ahead.
Well, it would be better if I turned my speaker on. Can you hear me now? I think so.
Great.
I went on for quite a time there. But anyway, thank you, Sharon Terry and Genetic Alliance, for this opportunity to talk with you about my recent work and to provide a learning opportunity that sharply contrasts to recommendation 2, especially in ways that security differs from privacy. That is, it's not a matter of always breaking into the data, but it may be the way the data are made available or captured. So let me describe the recent experiment and then report on lessons learned. The webpage that you see provides a summary of the experiment. We put names and contact information to genomic and medical profiles of participants in the Personal Genome Project. And by doing so, we correctly identified 97% of those profiles for which we provided names. Now, this experiment offers us a lot of contrast points to recommendation 2, and we'll talk about those in just a moment. But one of the most important ones is that the individuals voluntarily made their information available on the website. So launched in 2006, the Personal Genome Project aims to sequence the genotypic and phenotypic information of 100,000 volunteers and display it publicly online in an extensive public database. The PGP operates under a privacy protocol that it terms open consent. That is, individual volunteers freely choose to disclose as much personal data as they want, often including identifying demographic data, such as date of birth and postal code or zip code. Online, the profiles appear in a kind of de-identified state. That is, they don't have any direct appearance of the participant's name or address. The result provides volunteers with a sense of with what seems to be anonymity. PGP participants are required to sign a range of consent forms and pass an entrance exam. The consent form does not in any way guarantee participants a degree of privacy. To the contrary, the form explicitly states that participation may even reveal other non-disclosed information. The result is not that these participants do not care about privacy, but that these participants assume all the privacy risk when sharing their information. Once a participant uploads information to his online profile, the PGP offers almost no means to amend or modify the information. So participants basically display all the content of their profile or none at all unless they have expertise in editing. So let me now just give you the summary very quickly of the experiment and then talk about the lessons learned as it relates to recommendation 2. So we examined 1,100 publicly available profiles copied directly from the PGP website. About half of them had date of birth, gender, and a 5-digit zip code. Our experiment basically determined how many of those profiles could we re-identify by name using public records. So we purchased voter registration data from a third-party data broker, and we made a purchase of subscription to a public records website. And we used those to relate zip code, birth date, and gender to put back name to the PGP profiles. And notice that correctly identifying the participants was not based on the person's genome at all in this experiment, but on other information that appeared with the genome. In 1997, I had showed how these same demographics could uniquely identify most of the population in the United States. The finding is actually cited in the preamble of the privacy rule of the Health Information Portability and Accountability Act, HIPAA. So if these profiles had had to adhere to HIPAA, only the year of birth would have been released, thereby dropping re-identification significantly, though still not being zero. So here are the lessons learned. First, individual choice. The freedom to decide with whom to share one's own medical and genomic information seems critical to protecting personal privacy in today's data-rich network society. Individuals are often in the best position to make decisions about sharing extensive amounts of personal information for many worthy purposes like research. A person can weigh harms and benefits as relevant to her own life. In comparison, decisions by policymakers and committees are one-size-fits-all. But today's technology can allow much more nuanced decisions. The second point is that individuals are not likely to know the risk any better than trained experts. So it's not surprising that participants made poor decisions about sharing their demographics. Clearly, using year of birth rather than month, day, and year dramatically reduces their re-identification risk with minimal reduction in data utility. But the option to lower the risk was not available to them easily. Once a participant uploaded their information online, the PGP itself offered almost no means to amend or modify the information. The participant basically had to display all the contents or none at all, or have the expertise to do the editing. So part of what we did was we did make redaction options available to participants, and we offered them a way to learn how unique their demographics can be. In fact, the link that you see on this page, you can run the server for yourself to see how unique yours may be. So more generally, this experiment recommends the following practices. A person should know when his data is in a genomic data set so he can assess his risk. So the recommendation deals with genomic data sets, not necessarily where the person is the volunteer. In fact, the assumption throughout the recommendation is that the data set is somehow otherwise assembled and there might be consent. But regardless, a person should explicitly know when his data is in a genomic data set. Secondly, a person should be able to remove his data from a data set. Third, a person should know all the entities who have received a copy of his data. And fourth, a person should have a right to annotate, though not necessarily change his data. These are the kinds of practices that many of us already enjoy with our credit reports. but here they're adapted to these specifics. In conclusion, recommendation number 2 relies on old practices and old approaches. We don't ask police to keep using muskets because they did so many decades before. And we don't ask them to keep using muskets because they've offered us pass protections while others are using fast-action pistols. Similarly, is the same with privacy. We need to be able to have nimble approaches that can leverage technological advancement. Thank you.
Thanks very much, Latonya. We're going to move right away to the other 2 speakers and then leave time for questions. Again, feel free to type those in as you are listening. Thanks very much. And I should note that some of our speakers are using slides and some are not. So for Latonya, you saw the web page that she invited us to, in fact, look at, for example, how we can test our demographics, etc. So now we'll have Dr. Dixie Baker, and Dixie does have slides. She's a senior partner at Martin Blanc and Associates, and formerly of SAIC. Dixie?
All right. Good morning to everybody. I want to thank the Genetic Alliance and Sharon for inviting me to participate in this webinar. Securing whole genome sequence data is obviously very important. If we do it well, it can serve to improve the quality of health care and accelerate progress in biomedical science. If we don't do it well, it not only will cause harm to the individuals whose sequences have been exposed, corrupted, or destroyed, but also will create distrust that can hamper care delivery and scientific discovery. Today I'm going to discuss 5 points that were made in the Privacy and Progress report that I agree with, and 3 points that I want to challenge, and then close with a few final thoughts. First, let me address some points that I agree with. Clearly, absolute privacy is not possible. Similarly, when it comes to securing information, there are no guarantees because new vulnerabilities are discovered every day and threats are becoming more creative and determined and well-funded. Also, some of the vulnerabilities related to the genome are virtually impossible to eliminate since DNA can be found anywhere. There are no foolproof or guaranteed protection schemes, so the key is to understand the risk and to manage them, which echoes the recommendations that Latonya just talked about. Second, I agree with the report in its recognition that whole genome sequence data present the highest privacy risks of any medical information, and that these risks accrue to both the patient and her blood relatives. Also, both the sensitivity and the value of genomic data will vary over time and context. Third, the report makes an important point of noting that the clear separation that we've maintained between research and clinical context is disappearing, as the learning health system creates a dynamic synergy between healthcare and biomedical research. This is a really good thing for everyone, but we need to make sure that the security protections are consistent across the clinical and research contexts. There is no question that strong security protections combined with policies that enable consumers to exercise choice together engenders trust. However, to make consumer choices meaningful, we need technology to electronically record these choices using standards that will enable the technology that manages the data to enforce the rules associated with those choices. Currently, EHR, electronic health record technology, certification does not require this capability or prescribe standards for electronically capturing and sharing consumer consents. We also need legal protections that comprehensively cover all potential areas of genetic discrimination. And then finally, the report recognizes that any policy and regulations need to be agile enough to withstand advances in both biomedical science and in information technology. Okay, now on to the points that I'd like to challenge with the committee that wrote the report. First is the assertion that the possession of a whole genome sequence alone, without the demographic and phenotypic data, affords something they call practical obscurity. Many years ago, the security community abandoned the notion of obscurity as a protection mechanism, and today only refers pejoratively to the term security by obscurity. Persisting whole genome sequence data separately from their individual identifiers can at most provide an inconvenience and may serve as a challenge to those who specialize in circumventing false safeguards like obscurity. An individual's whole genome sequence is unique to that individual, making it an ideal biometric identifier, which is one of the 18 identifiers enumerated in the HIPAA privacy rule. As I mentioned earlier, separating a sequence from what the report calls traditional identifiers does make it more challenging to associate it with the individual it represents. However, a sequence includes many clues that help narrow down the identity possibilities. For example, the presence or absence of a Y chromosome can reduce the possibilities by about 50%, and coding of visible genetic characteristics and sets of genes commonly associated with heritage can further reduce the possibilities. Also, and especially, the current big data analytic technologies are becoming increasingly expert at extracting intelligence from very large volumes of data. And I think anybody who's ever used Google certainly can understand this. And the experiment that Latonya just reported also reflects that. In fact, Latonya has vast experience demonstrating exactly this point. The second point I might challenge is the report's categorization of 3 types of availability of whole genome sequence data: possession, access, and use, based on risk from highest to lowest. I think this categorization may be overly simplistic, and because it overlooks some important considerations that have a significant impact on risk. The report defines possession as holding a copy of a whole genome sequence that is accessible at any time. Access is defined as the ability to manipulate and work with the data without possessing a copy of the data file. And the lowest risk is use, or the ability to query for answers without requiring direct access to the data file or database. For example, one might submit a query to a service that would then analyze the data and return a response. Now, these definitions assume several things, and basically underlying these definitions are the assumptions that the possessed data are unencrypted, that access involves the flow of data bits, and that use involves querying a database of genomic data. One can reduce the risk of possessing whole genome sequence data to some degree by removing what the report calls traditional identifiers. Further, one can dramatically reduce risk associated by possession by encrypting the data. Of course, the degree of risk reduction is based on a number of factors, including the strength of the encryption algorithm, the strength of the key, how the key is protected, and how the encryption is integrated. For example, by encrypting genomic data using a strong algorithm and an encryption key that only the owner holds, one can safely store or transmit or transport the data anywhere. In a similar way, access need not imply data flow. Increasingly, healthcare organizations are implementing means of viewing data without the actual data bits flowing from their source database to the user's device. In fact, this is the kind of technology that allows me to show you my desktop without sending this presentation file to you. Use, too, can be implemented in different ways. Here I show the possibility of querying a metadata index instead of the database itself. This is the approach the President's Council of Advisors on Science and Technology, or PCAST, suggested in their Path Forward report. Consistent with the HIPAA privacy rule's minimum necessary rule and the broader security engineering least privilege principle, one should always select the approach that fulfills the need with the lowest risk. Security protections for genomic data should consider all potential data states, flows, and uses, and should provide continuous protection commensurate with the associated risks. The final point I would challenge is the report's claim that complete destruction of whole genome sequence data is likely impossible because during the course of a research project, the data get downloaded to various computers and servers, making it impossible to clean up afterwards. This may be the current state of affairs, pardon me, but it is not a technology limitation. Commonly accepted practices in disciplined project management and information management have dealt with this issue successfully for decades. The research community only needs to adopt these more sanitary practices. Again, minimum necessary enforcement is essential. In addition to my comments regarding specific points made in the report, I offer these 3 recommendations. First, the HIPAA security provisions legally apply only to healthcare entities involved in insurance claim transactions. The applicability of these provisions should be extended to all holders of individually identifiable health information. Second, the Genetic Information Non-Discrimination Act, or GINA, provides valuable protections against genetic discrimination in employment and health insurance, and these protections need to be extended across all potential uses of genomic data. And finally, the current standards for certifying EHRs for meaningful use do not address genomic data. As we move forward, the learning health system, it's critical that EHRs be capable of incorporating genomic data into health records and genetic knowledge into clinical decision support rules. Thank you.
Thanks very much, Dixie. And finally, we'll hear from Dr. Yaniv Ehrlich, and he's the Andrea and Paul Heafy Family Fellow at the Whitehead Institute for Biomedical Research. Yaniv?
Thank you very much, Sharon, and thank you for, I would like to thank the Genetic Alliance for giving me the opportunity to present our recent research in this area. I would like to start my talk and to remind everyone the value of public data sets in genomics. So just in my small group at the Whitehead Institute in the last 2-3 years, we were able to find the genetic basis of 2 devastating neurological disorders by combining sequencing data from patients together with public resources such as the 1,000 Genomes project. And by this process, we could give hope for families and for children. So, but I really I like what Dixie said, that if we're not going to do that right, then we're going to hamper public trust and we'll not be able to have these public data sets available. And this is the main motivation for the current experiments that I'm going to describe, where we try to map the risks in sharing genetic information. So about a decade ago, it has been recognized that there is co-segregation between surnames and the Y chromosome. For instance, if we have here the Smith family and they have a son, then the father will give the son his Y chromosome, and in most Western society, he also will give him his surname. Now, if this son is getting married and also has a son, he will give him his Y chromosome and also his surname. And this process will continue and will only break up by explicit surname conversions, non-paternity events, and mutations. Recreational genetic genealogy companies took advantage over this process, and they now offer services where they will send you a swab to sample the DNA from your cheek. You will put it in an envelope with $200, very important, and then you will send it to these companies, and then they will genotype a series of short tandem repeats, STRs, on your Y chromosome, and will upload the results into a database. And what I'm showing you over here are my own test results in a database called ysearch.org, and you can see my surname and the list of markers on my Y chromosome. And people do this process because it's a lot of fun. You can meet, you can connect with your patrilineal relatives, you can meet the black sheep in your family, and so on. So we try to test to see if we can use these databases in order to infer the surnames from whole genome sequencing data and to combine it with other information and really re-identify individuals. So let me show you now an example with Craig Venter. So we took Craig Venter whole genome sequencing from the NCBI website. We profiled the short tandem repeats on his Y chromosome with a tool that we developed about a year ago in my own group called Lobster. And using this tool, we found different markers on his Y chromosome. We went to a database called ysearch.org, available online to each one of the attendees in this webinar, or anyone that has an internet connection. And in this database, basically each time that we identified a marker, we just inserted it to the search interface. So for instance, the DYS458 that has 17 repeats, we just place it in the search mechanism together with all the other alleles that we identified. And then we simply clicked search on this web page. And after a few seconds, what we found was the name Venter was the top match in this search. If you want to try it yourself, you can go to this link, bit.ly Craig_Venter_haplotype_updated. It will redirect you to ysearch.org, to this web page. We already filled for you all the markers from Craig Venter genome. You can click search and see that you get Venter as a top match. So what I want to show you that in this case, what I just showed you, that we took whole genome sequencing data and we got a surname by just analyzing the Y chromosome of Craig Venter. Now, of course, right now we just have Venter, but the question is, can we get to Craig Venter by knowing that this is the surname Venter? And the answer is yes. What we did, based on the genomic data, we infer the surname, Venter, and we infer that this person is a male because he has a Y chromosome, of course. Then also, according to the HIPAA privacy rule, and Latonya mentioned that, the state and age are not considered as identifiers, and they are found in some genomic databases. So using the combination of Venter, male, person that lives in California and born in 1946, we went to ussearch.com. It's a public record search engine, and you can try it yourself. And what we found was that we had two matches, including Craig Venter himself, using this information. So we can get from whole genome sequencing data into a surname, combine it with demographic information that is not considered identifiers by the HIPAA privacy rule, and get to an individual. But of course, in this process, we knew that Craig Venter is Craig Venter, and we wanted to see if we can find anonymous individuals from their whole genome sequencing data. So we focused on the 1,000 Genomes project because the people over there were consented that a privacy breach might occur in the future. We downloaded 10 genomes from the Utah populations over there, and we did the same process. We analyzed these genomes using Lobster to infer the short tandem repeats on the Y chromosome. We went to two public databases and inserted these markers and searched. And what we got was, we got that from the 10 genomes, we had 8 surname predictions of people with Utah ancestry, which suggests that we were right with at least some of them. And then we focused on this pedigree that I show right here. Now, this is a 3-generation pedigree. Almost all the pedigrees of the CU genomes has 3 generations. And we identified the surnames of the 2 people in black, the surname of the paternal grandfather and the surname of the maternal grandfather. So we had 2 surnames in hand. Then we just went to Google, and we did a very similar search to what I'm showing you over here. We don't really release the exact details, but it's something very similar. We searched in Google with a surname and the location, and we found an obituary that had that contained the exact description of the family in Corial. It had the same number of kids as expected. it had the same order of males and females as expected, and this is a quite large family. And it's very unlikely to see the same order of girls and boys. The surname of the father matched the surname of the paternal grandfather. The maiden name of the mother matched the surname of the maternal grandfather. And this family is from Utah, and all the people lived in 1984, the time that the DNA was collected, including the grandparents. And the chances that we found this pedigree by random match is close to 10 to the minus 9 after scanning all households in the US. Now, of course, this is only one family, and the question is this just some, beginner's luck? Can we replicate this result? And the answer is yes. We did the same process for another family from the CU individuals and another family. And by this process, we identified all the people that are listed here in black in this 3-generation family. Their genomes has been, or the genomes and their gene expression and other genetic information was studied quite extensively the past 20, 30 years. And in fact, we had so much information that we can connect between the people that donated their samples to the recreational genealogy databases, here in red, to the people that participated in the 1,000 Genomes project. So what you see, for instance, in the family in the middle, you see that we have the second cousin once removed participated in recreational genealogy testing, and using that we could identify his entire family. And so we have very distant relationships. So in total, we've reached a privacy of close to 50 CU samples in this collection. So just to summarize what I just showed you, I showed you an approach that there is no experimental work involved. We just used computational tools. If you have an internet connection and a good server, you can replicate what we presented. We showed that the identifying information is can be inferred using these deep genealogical ties. You don't need the same person in the database. And everything here relies on public resources. And in total, we had several layers of evidence using inferring the surnames of 1,000 Y chromosomes, a set of experiments that I didn't describe in this short presentation, the identification of enter, and the identification of the clones of 50 CU individuals. So my recommendations are as follows. First, I think that when we consent individuals to participate in genetic studies, we should be honest about the risks, that it's very hard to de-identify the information. But we should also be honest about the benefits, and we should remind people about this terrific endeavor called human genetics and how it saved the life of people. Just today we learned about Angelina Jolie and her BRCA1 mutation. This type of process was not, we will not be able to be in that point without the families of the HapMap or the CU individuals that contributed the DNA for genetic studies. I also suggest that we'll develop this multi-level approach where participants can decide how to share the data, if they want that the data will be in some public database or some limited access database, or something in between that. Also, I think that we should maintain this proactive approach of keep mapping the risks. It's better to know and to do this genome hacking in a friendly way to understand the risk than that at some point in the future it will happen to us without knowing that and without any solutions to the participants. And my fourth recommendation is to invest more in technical solutions. I think we are giving up too fast on our ability to maintain privacy using technical means, for instance, using encryption or other techniques. And maybe by investing more in that area, we could really get, we can better protect our participants. I'd just like to thank the really terrific group that I was fortunate to work with on this project. Thank you.
Thank you very much. Excellent presentations all, and we do have a number of questions, but before we go to the questions, I want to give you three the opportunity to speak to one another, to ask any questions or clarifications or add something that you didn't say in your original presentation. Feel free to go ahead. Your three lines are open. I'm assuming that either you're having trouble getting off mute. Go ahead.
Yeah, this is Dixie Baker. I just wanted to commend Janov on his presentation and say that I certainly agree with his recommendations, and I certainly agree that the benefits are huge, but that if we don't do this right, it can really be harmful. I also would like to point out that his recommendations really are very consistent with the fair information practices principles, and I think that it's really important. We talk a lot about informed consent, which is obviously important, but fair information practices are also very, very important, like transparency and being honest with people about the risks and the benefits. You can gain an enormous amount of trust from individuals by being honest with them and upfront with them.
Great, thanks, Dixie. Janov or Latonya, any other comments, questions for each other? Okay, let's go to some of the questions that have come in. One was simply applause for all of you, so I think you should all take a bow. That was terrific. A couple are asking similar questions, and so I'm going to put a few of them together. One questioner asks if you could talk more about the recommendation that security approaches remain nimble and responsive, but at the same time, for example, Latonya, you said that professional ethical standards are outdated. So how can we retain a sort of nimbleness and responsiveness and have them be either with updated ethical standards or with a new set of ethical standards? A similar question was about policy changes that suggest some major shifts and who should be involved in such policy changes. So I think if we can talk a little bit about approaches and standards and ethics and how those integrate, and any of the three of you could please comment on that. Maybe Latonya, you can start.
Sure, I'd be delighted to. So one of the problems with the past practices that we inherit is that they make very blanket end-all positions. So something as simple as saying that a person, so for example, the ability to just give accountability back can be quite impressive for individuals who are trying to assess risk. So that's just simply being able to have some low-hanging way an individual gets access. And the PGP, since I use that as an example, is publicly accessible, but they could simply have a simple registration. So the data is freely available, but you have to provide at least an email or something like that. And that way an individual could have a sense of knowing, well, I found this new vulnerability, to whom am I vulnerable? Or if the data weren't publicly available, if there is a breach, individuals wouldn't even know that they're vulnerable because they wouldn't know their data are there. And if they know their data are there, then how would they know whether or not that person got it? And so there's a lot of very low-hanging technologies, but our rules, by saying, no, all we need is consent, all we need is a data use agreement, wipes right over it. And I could give like 12 to 15 more examples of low-hanging technology that could be merged into policy, but when we rely on old policy alone, we just tend to wipe right over it.
Thanks. Dixie or Janov, any other comments on that question?
Yeah, this is something I mentioned, and this is Dixie. I mentioned in my presentation. I think that I think that the HIPAA security rule is a good example of how you can build certainly an example of an earnest effort to build a regulation that has some nimbleness built into it, and it does that by its heavy reliance on risk management, risk assessment, risk management, and implementation of reasonable and effective, measures for an individual situation. Unfortunately, so it's all based on risk management. Unfortunately, we find in the real, once we collect data on how many organizations are actually performing risk assessment and basing their HIPAA implementation on risk, we find that that number is pretty low. But as a technique, I think it does a really good job of approaching it in a way that at least it can be responsive to technology. As new technologies come about, you still, assess the risk and implement measures to counter those risks or to effectively manage those risks. And I also think with respect to policy, and I'm a more technology person than policy, but I will say that with respect to policy, I think that we tend to really think of informed consent as the answer to every single question that comes up. And I think that it has to be a balance among the technical protections, the fair information practices that I mentioned earlier, informed consent, and legal protections that is a fallback. If and when things go wrong, you still have the legal protections that people, that can't be discriminated against, even if the technical and policy measures fail.
Great, thanks very much. Question for
this is Latonya.
Yeah.
Yeah, this is Latonya. I just wanted to follow up with Dixie a little bit there. I like very much the idea of risk assessment and risk management as a way forward to figure out the best ways to integrate policy and technology. But the privacy rule, which is separate from the security rule, in some ways, the way the panel is set up, it sort of merges these two, conflates them as if they're the same. And security and privacy, when it comes to recommendation 2, are actually not the same. So there are many things that I can do under the security rule but the kinds of examples that both Janif and I both talked about are not in the security rule but in the privacy rule. No one broke into this data, no one broke into a machine, nor was there a breach. It was simply a matter of the data that's given away and assumptions made by policies and procedures about that data. And so that's on the privacy rule side. And so risk assessment on the privacy rule side would be very, very helpful, but that's not how that rule is framed.
I couldn't agree with you more. That's why recommendation 2 is about security. So I tried to really, respond to the security question. But I can't agree with you more that there isn't enough flexibility in the privacy rule, and in particular the 18 data elements that are, cast in stone in regulation. When we know that our, big data technology can, as has been demonstrated here today, can really get by those. So I agree with you there, Tanya.
Yeah. And let me just say, I'm sorry.
Yeah, if I can just add, to the whole notion of security assessment for genetic privacy, and I'm sure that Latonya, you also experienced that there is some pushback from the community. If it's, what are the ethical grounds to do these risk assessments, right? And some people, in fact, prefer not to know than to know. And you conduct these experiments, you report them to people, and before we publish them, I got a major pushback from quite senior people in our community in human genetics, if this is a smart thing to do or not, because some people view that by investigating these risks, that you are in fact creating these risks. And I completely disagree with that. I think if you look at the computer security industry, bank security, all of them, they employ quite extensively vulnerability testing just to make sure that the data is well protected. And I think we should adopt very similar guidelines and very similar practices to test our own databases. But this is something that not many researchers are willing to work in that area because of this pushback from the community.
Janif, let me just applaud your comment. As you know, I feel very strongly the same way. It's extremely important that the risks be made publicly available and be able to be exposed, because if they're not exposed, it doesn't mean they don't exist. And what happens is eventually some commercial entity will exploit that risk and generate a revenue stream that uses that risk. And society marches on without knowing until it's way too late. So we're definitely better off. Computer security has done this too with encryption. You know, at first, encryption schemes were just made up ad hoc schemes, and then somebody would break it and publish that they broke it, then somebody would develop a better one. And this cycle just continued until we get the strong forms of encryption that we enjoy today. And I think exactly the same thing will happen here in privacy if we can let that cycle happen.
Yeah, I totally agree. This is very consistent with what I said earlier about the, practical obscurity. I just think that's, head in the sand type of thinking, and we've got to be honest with people. I do agree that people should be able to say, I don't want to know all of the indicators in my genome sequence, but that's different. The security risks should be available to people, or their informed consent is certainly not informed.
Great, thank you for that interchange. So we have some questions about HIPAA coming off the beginning of your exchange. Are you suggesting, and particularly Latonya, that institutions with access to whole genome sequencing use HIPAA-like security protections, or actually, and I think there's some confusion there about security and privacy, or actually become HIPAA entities and held to HIPAA regulations? And then related to that, someone commented, HIPAA is not nimble and does not provide for a flexible environment for research to be innovative or collaborative. It requires consent for every disclosure, which can be costly and hindering. So,
But that comment, oh, I'm sorry.
Oh, go ahead, Dixie.
That comment, the comment that I made in my presentation and earlier about the HIPAA being nimble, I said the HIPAA security rule, and as we just went through the conversation, we're not talking about nimbleness with respect to the privacy rule, and we should be very, very explicit about that.
Great. Anything from any of the others on that?
Yeah, that's all I was going to say as well.
Okay, super.
Yeah, I totally.
Great. So we have some questions about the assumption that someone presumed you made, Latonya, and I think, again, this can be opened up to everyone, but maybe starting with you, that the PGP participants wanted to keep their participation private, and that, in fact, they had, and I'm one of them, and I think my data set was actually in the set that you used, that they had been through an extensive consent process, and privacy perhaps was not important for some of them, and so can we assume that participants made educated decisions in the PGP and accepted that their genomic data would be or could be identified? And then in a related question, someone asked, could we explore the differences between privacy and autonomy? While we talk about preserving participants' privacy, should we instead also develop systems to increase participants' autonomy?
Yeah, I'll start with the first part. So one of the assumptions that I made about PGP participants is that not only had they gone through this training, but that in some sense they probably didn't really have the same view towards privacy that other people might, or the same sensitivity, and that had been a very big question. But when I looked at the blogs and the discussions that have happened among the participants since the re-identification experiment, two things become very clear. One is that while all of them seem aware that it could happen, the fact that it actually did happen made a big difference to many of them. It kind of jarred them. So it's not that they didn't know it could happen, but they discounted. So in the economics of privacy, there are tons of experiments, and this now is like one more of them that shows we as humans always do this discounting function, that will discount the risk as long as it's in the future or a possibility, but when it's made very explicit, it changes our equation. The other thing that was a surprise in interacting with the PGP participants at their annual conference was I was surprised I got about 3/4 of 3 out of every 4 participants who came to talk to us explicitly said thank you. And I found that profound. It was profound for 2 reasons. One, they clearly assumed the risk. They felt that participating in the PGP meant that they personally were now assuming the risk, and the thank you was simply, thank you for letting me understand my risk better. And then, of course, their remedies were made transparent to respect to this attack. So it's been a real educational experience working with the PGP.
Terrific. And again, as you've said previously, the 3 of you, it's good for us to have at least data sets like these that we know we can use and improve. So vis-a-vis that sort of question, we have a couple questions around gender and pedigrees and masking, and I'm not sure if this is more of an obscuring kind of technique, but for example, someone wants to know, Yaniv, can you do the same procedure for females because you don't have the Y chromosome? And then a couple other gender-related questions or comments. One suggestion is to mask pedigrees by not including gender, or in fact adding or subtracting SIBs in the wrong or additional SIBs order. And then also, could you actually confirm identity of the participants that you guys unmasked directly, or did you rely only on statistics? So a lot of questions there, but
yeah.
basically, if you talk ahead.
Okay, so I will start with the more easy ones. So we decided deliberately not to contact any of the people that we identified because we never consented them, we don't know them, and the last thing we wanted to do is to really stress them or single them out of this group of hundreds of people that are part of the CU panel. So we decided not to do that, and it was not proof, but the p-values that we obtained, the probability of an error were extremely small compared to other genetic studies. And also we identified Venter, and also we identified close to 1,000 other people. We tested another 1,000 chromosomes that we knew their surname is part of the manuscript. And now there was another question about masking the gender. It's impossible because once you have the genetic information, you can see if you have the Y chromosome or not. So this will never really help you to know the gender. Even if you mask the Y chromosome, you can see if you have 2 or 1 X chromosomes, and this will not help you. So gender masking is impossible, I would say. Now about the pedigree structure, what the NIH decided to do was to take away the ages of the people. So essentially kind of like randomizing in a way the order of males and females. It's not completely. It helps, but it doesn't help completely. You can still, even without this information, since the probabilities were so small, you can still rely and you can still infer that you got the right individuals with what you have. So it helps, but it's not enough, but it really helps. The first question was, what about females? So our approach doesn't work directly on females. The way that we identify the females was by finding the males, and since they're part of the same study, we could infer the females. With our approach, if I just see a female genome, I cannot infer the surname of this genome. However, I want to remind everyone that we just described one approach. There are many other approaches that could work on genomic sequences. There is a growing industry of recreational genetic genealogy, recreational genetics, that people share a lot of information. So it might be that in the future there will be other techniques that will use public genetic data and will match it to genomes that are part of studies that are not through the Y chromosome but through other means.
Great. And Yaniv, any response? Oh, go ahead, Latonya.
Well, I was going to, if you have to talk to Yaniv directly, you should go ahead. I was going to just respond to the scoring on the PGP side.
Okay, so just a quick follow-up. Have you received, Yaniv, any response from anybody in the Utah population directly?
Not directly. We contacted before the study was even accepted. we went to all the stakeholders, any stakeholder in the community that we can think of, and presented the results and let them know, because we didn't want to create any stress on these people in the day of the publication. We want to take care of everything before that. We presented the results to the head of the Human Genetics Department in the University of Utah, Lynn Jordy, and also to the head of the IRB of the University of Utah. We presented it to the NHGRI, to the people in the 1,000 Genomes. And I know that the University of Utah, they considered to contact the families, and I think they decided not to contact them just because there are about 40 families in this study. We identified 3 out of them. They didn't want to single out any of the families or to stress all the others. They just, the NIH just took the ages out, and that's it, according to the best of my knowledge.
Great. Latonya?
Yes, with respect to the PGP, we had 2 advantages with respect to scoring the results. The first one was that in some of the profiles, when the sequence data was in a compressed file, when you uncompress the file, it often sometimes would expose the name, or the name might be the person's name might be embedded in a PDF file. So for some of them, we actually found the names elsewhere. But regardless of whether we found the name or not, we still submitted our results to the PGP staff, who did do the scoring for us.
Great. And I'm going to close with a more global, literally global question. And then we do realize we have several other questions, and again, we will try to get answers to those, because I think our speakers are amenable to continuing this conversation even offline. So the question here is, and this is just an example, but for example, BGI recently acquired Complete Genomics, and as part of the process, the deal was reviewed by the U.S. government to analyze potential privacy issues stemming from a Chinese company with some government ties controlling data on the genomes of American citizens. The deal, as we know, was ultimately approved. How does the global nature of the genome sequencing industry, because this is probably just a start, and there are probably, in fact, other companies that have global reach, how does that impact recommendations around security and privacy? And I realize that's a huge question, but if each of you could comment on that, we'll make this the last question for our webinar today.
This is Latonya. I'll go first then. The problem with when the genomes and information like that go overseas, if you're relying on a regulation, that regulation is not enforceable off our borders. And so that's one problem. If your protection is in policy, then you may have a serious problem. The other problem too with genomic information can be a national security issue. If the data can be re-identified and also give us predictions of disease and so forth, individuals could end up being compromised if they're in a key position, like in the military or elsewhere. And so I would also worry a little bit about those kinds of national security consequences if it turns out that overseas is a large number of genomic information for which predictions could be made and the individuals actually identified and contacted.
Oh, this is Dixie. I agree with Latonya, and I would go one step further to point out that not only are our regulations not enforceable, but regulations, law and regulations and social values vary considerably throughout the world. So you certainly can't make any assumptions at all about how information will be protected across different countries.
Yes. So I agree with Latonya and Dixie, and I would like to add that our study showed that it's not only that you can identify, once you accumulate information about genomic sequences, you not only identify these people, but you can identify very far relatives of these people. So basically, by accumulating even modest amount of whole genome sequencing data by foreign entities, they can identify a large number of U.S. citizens using this approach. And this is something to think of.
Right. Great.
Yeah.
Well, thank you all very much. This has been really, really rich. We got quite a few other people just commenting that this has been a fabulous webinar. We could probably do this for 2 or 3 hours. So I want to thank you again all for your work as well as for presenting today with us. You can see on your screen now to our participants that on June 11th we'll have recommendation 3 at noon that day. Our speakers that day will be Amy McGuire, Susan Wolf, and John Wilbanks. Again, thank you all very much, and especially thanks to our webinar presenters. Have a good afternoon.